Rust is a programming language like C, C++, Python, Java, and so on. It was built as a systems language with a focus on safety and speed. As a result, it is a natural fit for embedded systems with a few caveats that we'll look at. The goal of this series is to get you up and running with Rust on embedded systems, which means learning a new language while learning the basic constructs for writing small, efficient microcontroller code. If you want to simply jump in and get your hands dirty, feel free to go to the end of this episode where we set up the Docker image and build Hello World before skipping to the next video where we write a basic blinking LED app. Let's see what we'll cover in this whole series. I would not recommend jumping into this series if it's your first time with embedded systems, as Rust is still relatively new and can be tricky to get working with microcontrollers. You also have to learn a new language on top of learning the embedded parts, and I will honestly say that Rust has a steeper learning curve than, say, Python. So it helps if you have some experience working with microcontrollers. That might mean you're comfortable with Arduino, MicroPython, or CircuitPython. Even better, you've made some projects in C or C++ with silicon vendor tools like STM32 or ESP-IDF. You should understand some memory management concepts like stack versus heap and how pointers work in C. Rust builds on these concepts with its ownership model, so it helps to be familiar with them before tackling Rust. If you've worked through either my Getting Started with STM32 series or my Introduction to RTOS series, you're probably ready to tackle embedded Rust. I don't want to spend the whole series just talking about the language, and I don't want to assume you're already familiar with the language to just focus on the embedded side. So I'm going to do a mix of the two. I'll assume you're familiar with some embedded concepts, but probably haven't used Rust yet. So in between some of the episodes, I'll recommend that you read parts of the Rust book and try some hands-on exercises to get familiar with the language. That way we can focus on the embedded stuff in the videos while learning Rust at the same time. The Rust programming language, also lovingly known as the Rust book or just the book, is the official online guide for learning Rust. It's maintained by the Rust team, and in my experience, it's the best guide for understanding the language. Even better, Brown University maintains an interactive version with quizzes to test your knowledge. I actually recommend working through that version, but just be aware that some of the quiz questions can be quite tricky. In between some of the videos, I'll recommend reading certain chapters from this book, as we'll build on the knowledge from them for the following episode. While I'll describe a number of the concepts in the videos, know that this book goes into a lot more detail, which allows me to focus on the embedded side of things in those videos. For example, I might say read chapters 5 through 9 before an episode where we start working on our own I2C driver. That way, you have some familiarity with the concepts like structs, enums, and error handling before seeing an example. Just so you know, I'll be using the 2024 edition of Rust and the 2024 edition of the book for the series. In addition, I'll also recommend working through a few hands-on examples using the Rustlings framework. I'll make sure it's pre-installed in the Docker image so you can start right away. While the book talks about the language from a conceptual perspective, the exercises in Rustlings are great for trying your hand at actual implementation and debugging. It's the perfect companion to the book, and like with the recommended chapters, I'll also recommend groups of Rustlings exercises to perform prior to the next video. Let's talk about what we'll cover in this series. My goal is to introduce the Rust language piece by piece, while also giving you the building blocks needed to start creating your own embedded projects. To do that, I'll interleave embedded examples with non-embedded examples, while also recommending various chapters from the Rust book to read in between episodes. In this episode, we'll look at the history of the Rust language, why you might consider using it, and why you might consider using it for specifically embedded systems. I'll also show you how to install the Docker image that goes along with the series, should you wish to follow along with a unified development environment. We'll also run a simple Hello World program so you can see how to build Rust programs for computers with full operating systems. Before moving to episode 2, I recommend reading chapters 1, 2, and 3 in the Rust book. That will give you an introduction to the language and cover some basic things like types, functions, and control flow. In the second episode, we'll create a simple blinking LED program. Note that there will be a lot of boilerplate code we need to write in episode 2 to get even a simple blinky program to run on our microcontroller. Don't worry if not all of it makes sense. We will build future programs on top of it that demonstrate concepts you read about in the Rust book. A similar kind of thing happens in the third episode. We will use some available libraries to pipe data out over serial via USB. This will make debugging much easier going forward without relying on a separate piece of hardware like the Raspberry Pi debug probe. Where possible, in these 3 episodes, I'll point out Rust concepts that you read about in the first few chapters of the book. But the main intention is to get a template that we can use to build demos going forward. Note that this is all done with bare metal programs and some third-party libraries. I found that frameworks like Embassy rely on more advanced Rust concepts to even start using, so we save that for the very end of the series. I recommend reading chapter 4 in the book before the 4th episode, where we'll talk about the main ownership and borrowing rules in Rust. As with the original Hello World example, we won't touch embedded code here, but I still think it's important to review these rules as they can be tricky to grasp. From there, you should read chapters 5 through 9 as they go into structs, enums, managing crates, and error handling. We'll see some of those in use as we create a basic I2C driver to read from a temperature sensor in the 5th episode. Then, I recommend reading chapter 10, parts 1 and 2. These cover generics and traits, which we'll review in episode 6. We'll just look at some very simple Rust examples here that aren't necessarily unique to embedded code. Then in episode 7, we'll wrap up our I2C sensor driver into a library that you can import into your various applications. After that, I recommend finishing chapter 10, which talks about lifetimes. We'll cover some basic non-embedded examples. Chapter 11 of the Rust book talks about writing automated tests, which we'll review in episode 9 and discuss how that can apply to embedded systems. At this point, you should have a decent working knowledge of the Rust language, so we can dive into a few embedded specific concepts for the rest of the series. You're welcome to finish the book at this point, but we won't need it for the final few episodes. In the 10th episode, we'll look at handling hardware interrupts. In episode 11, I'll show you how to use the Raspberry Pi debug probe and GDB should you wish to use some more advanced debugging techniques in your project. Finally, we'll end with an example of how to create asynchronous tasks with the Embassy framework. Embassy comes with its own hardware abstraction layer, so all of that boilerplate and template code we wrote earlier won't help much here. But I found that using even basic functions in Embassy required a decent working knowledge of Rust. As a result, I recommend learning Rust with bare metal programs first before jumping to a framework like Embassy. That being said, I really do like Embassy, and once you try it, you may not want to go back to bare metal. Now, let's get started. Personally, I like knowing a little about the history to get a better understanding of why you might want to use something. So let's take a moment to learn how Rust came into being. To understand the reasoning behind Rust, let's look at a simple C example. If you've worked with C or C++ for a while, can you spot the issue? This seems pretty straightforward. We allocate a piece of memory on the heap to be the size of an integer. We then tell that memory to hold the value of 42. We might then do something with that value in our code. Later, like a good C programmer, we free up that piece of memory. If we didn't, we might inadvertently create a memory leak where you continually allocate memory without freeing it. This is also bad, as the program will just continue to consume more and more of your computer's memory until it eventually crashes. However, the issue comes in when we try to access that piece of memory later in order to, say, print it out. This is undefined behavior in C, which means that the language specification makes no guarantee about what will happen when this is compiled and run. It might print the original value if that chunk of memory was not overwritten by something else, or it might print something else if that memory was overwritten. or it might just crash the whole program. That's the idea behind undefined. The language itself makes no promises as to what happens in certain situations like this. Some compilers might catch it, but more often than not, you can spend hours debugging tricky runtime errors like this. Or worse, you ship the product and it randomly crashes for users or exposes nasty vulnerabilities for people to exploit. Microsoft estimated that some 70% of all security bugs are related to memory safety issues. This was exactly the inspiration that led Graydon Hoare to create Rust in 2006. While working at Mozilla, he noticed that the software running the elevator in his apartment building kept crashing, which required repeated visits from the maintenance crew. So he began creating a new programming language as a personal project. He hoped to prevent these types of runtime memory bugs by designing a language and compiler that explicitly prevented them without compromising on execution speed. He named the language Rust after a group of fungi that he said are over-engineered for survival. Graydon worked on the project for about 3 years before Mozilla took enough interest to officially sponsor it. They even placed a few developers on the project full-time as they bought into the vision of a memory-safe, fast language. By 2010, the ownership system was fully established. This is something we'll examine in depth in a later video, as it can be tricky for newcomers. The official Rust logo, an R surrounded by a bicycle chainring, was designed in 2011. The original Rust compiler was written in OCaml. By 2012, the team had fully rewritten the compiler in Rust, which makes it a self-hosted compiler. This coincided with the version 0.1 release of Rust. While Rust originally had a garbage collection system, it was used less and less. By 2013, the team fully removed the garbage collection system from the language and enforced the ownership system as the primary means of ensuring memory safety. Hoare also stepped down that year to let a more organic governing system evolve. Version 1.0 was released in 2015, which focused on stabilizing the core features and ensuring some level of backward compatibility with future releases. Due to the economic downturn from the COVID pandemic, Mozilla laid off some 250 employees and disbanded the team working on Servo. This was Mozilla's experimental browser engine written in Rust. This cast doubt on the future of Rust as a language. Luckily, the Rust team was able to generate enough interest in Rust that a full foundation formed in 2021, consisting of Amazon Web Services, Google, Huawei, Microsoft, and Mozilla. The Rust Foundation provides funding and oversight for the various Rust teams who implement and maintain various parts of the language and associated toolchains. As you can see, Rust has been around for a while, and it's still quite actively maintained. Let's examine a few reasons you might consider using Rust in your next project. We'll start by taking a look at how Rust provides memory safety assurances while maintaining execution speed. In general, most programming languages make a trade-off between two different memory management strategies. The first is manual memory management. Older, lower-level languages like C and C++ force users to allocate and deallocate memory manually. On the plus side, this usually means faster runtimes as there is no overhead for these kinds of operations. It also means predictable performance, as what you write is what gets executed, with some assumed compiler optimizations. It also means that your program sizes could be quite small, as there was no extra overhead for memory cleanup. This is why such languages, specifically C, are the most common in embedded systems. However, programmers need to know exactly what they're doing, as it's easy to create memory leaks or undefined behaviors in programs. To afford this kind of low-level control, such languages are often quite verbose, and developers need to track and debug memory allocations and deallocations, adding to development time and complexity. This means writing such programs can be slow and painstaking. Higher-level languages like Python, Java, and JavaScript attempt to address these potential memory bugs by adding something called the garbage collector. This is a system that runs automatically with your code to track memory allocations and frees up any memory that is no longer used. It's usually implemented as a separate thread or concurrent task that runs periodically and is often invisible to your code. It promises much better safety with fewer or no undefined behaviors when it comes to memory issues. Languages that use a garbage collector can often abstract away memory management so developers can focus on higher-level concepts. This means that such automatic cleanup can afford faster development times. However, this all comes at a cost. The garbage collector has overhead, both in runtime speed and creating a larger program size. It must periodically run, which costs processor time, and it's often difficult to enforce a particular collection schedule, which might mean unwanted pauses in your program. You also lose out on low-level memory control, which some programmers often want for low-level system development, like operating systems and microcontrollers. Starting in the late 90s, some companies, government, and academic institutions began introducing standards for low-level languages like C to enforce memory safety coding. The most popular is probably MISRA, which is used frequently in the automotive, aerospace, and medical industries. You might also come across Cert-C and ISO IEC TS 17961. These don't change the language or compiler. Rather, they provide a set of rules and guidelines that, if followed, can produce memory-safe code. However, they require teams and code reviews to ensure that such standards are followed. There are some tools that can check code for you, but it ultimately comes down to people enforcing the rules. For the longest time, manual memory management and garbage collection were the only two real paradigms for dealing with memory in the vast majority of languages. Rust provides a third option that it calls the ownership model. A few languages in the 90s and early 2000s introduced some early ownership concepts that became the basis for Rust's technique. These include the likes of Lolly, Linear Objects, MLKit, and Cyclone. However, these languages were often relegated to research projects and never made it into the mainstream. This model offers essentially the same benefits of manual memory management with the addition of guaranteeing some level of memory safety. Programs written with this model are often smaller and faster than similar programs written with a garbage collection system. I say smaller overhead here because Rust has a few minor runtime checks, like checking for out-of-bounds array accesses that introduce a slight runtime overhead. The downsides include slower development time due to the added complexity and the learning curve. I'll say that Rust is harder to learn than C, as you need to understand how the borrow checker system works with the compiler to enforce ownership in your code. So what is this ownership model? Rust has three basic rules when it comes to ownership. The first is that each value in Rust has a variable that acts as the owner of that value. The second is that there can only be one owner of a value at a time. And the third is when the owner goes out of scope, the value will be dropped. Let's look at a brief example in Rust. On the first line, the string hello is created on the heap and assigned to the variable s1. At this point, s1 has ownership of the value hello. Then we perform an ownership move on the second line. At this point, s2 is now the owner. If we try to print s1, the compiler would catch this and flag it as an error, as s1 is no longer an owner of anything. But we can print the contents of s2 as it is now the owner of the string. With this type of ownership enforcement, if we dropped or modified s2 after the reassignment, the shared piece of memory referenced by s1 would change. This is known as a dangling pointer. In another language, s1 would still be a valid variable, pointing to some now freed or modified piece of memory. Trying to print it might produce some unwanted behaviors or open a security vulnerability, like printing sensitive information that now resides in that section of memory. Let's say we wrap this snippet up into a tiny function called say hello. To address the third rule, we see that s2 would go out of scope after the function ends. As a result, Rust automatically drops the string value it owned and frees up the memory. This incurs a small amount of overhead to actually free the memory, and that's invisible to the developer. You do not have to manually call a free or drop function. This usually takes only a handful of clock cycles. Note that the standard library that comes with Rust is not completely deterministic for some overhead tasks like this cleanup, but you can create your own allocators or avoid heap allocation if you need hard real-time systems with complete determinism. This is just a very basic explanation of how ownership works in Rust, so you can start getting familiar with it. Things get more complicated when you start talking about references and borrowing. We'll spend an entire episode looking at ownership and borrowing, so don't worry if it's not quite making sense right now. While Rust is a general-purpose programming language, you'll often hear it advertised as a systems language. As we saw, it offers manual memory management, which allows for direct hardware control. You'll see Rust also offering zero-cost abstractions, which means that high-level features and libraries compile down to efficient machine code. The lack of garbage collection means that performance is fast and predictable, and it has support for inline assembly code when you need to write something optimized for a particular CPU architecture. That means it's a good fit for writing low-level operating system kernels, hardware drivers, game engines, web servers, and, as we'll explore in this series, applications for embedded systems. Even though Rust has been around for just about 20 years, it has only now just started gaining some adoption in various industries. If we look at GitHub's language popularity chart, based on the total count of unique developers making at least one Git push for a language, we can see that Rust has gone from rank 35 to 21 in about 5 years. That's a pretty impressive climb. We can also get a listing of companies that have begun adopting Rust for official projects. Notably, this includes things like AWS Firecracker, Microsoft's Azure IoT Edge, and some of BlackRock's projects for fintech. Tailscale, Bitwarden, and 1Password have started using it on some of their products. You'll also find it being used on new projects in the automotive, aerospace, and consumer electronics industries. Rust is also being integrated into the Linux kernel for writing device drivers and kernel modules as a second option to C. Microsoft is proactively rewriting core components in Rust to replace legacy C++ code. This is all very impressive, but what about for embedded systems? I mean, that's why you're watching this series, right? As you're probably aware, the embedded world moves much slower than the rest of the computing world, and as you can guess, Rust adoption is a bit slow. But it is happening, even if it's mostly community-supported projects right now. For example, a talented group of developers are adding Rust support to STM32 microcontrollers. ST has even started to offer official drivers written in Rust. ESP32 support is also mostly community-driven, but it does have some official support by Espressive. Raspberry Pi's RP2040 and RP2350 actually have impressively robust Rust support. While it's technically a community project, RPHAL has strong unofficial endorsement from Raspberry Pi. If you'd like to hear it from the man himself, here's Eben Upton, the CEO of Raspberry Pi Holdings, to tell you his thoughts on Rust.
Hi, I'm Eben from Raspberry Pi. It's wonderful to see Sean putting together this embedded Rust series, and we're delighted that he's chosen Raspberry Pi Pico 2 as his demonstration board. Rust offers some significant advantages for embedded development, particularly in areas of security and reliability. The built-in memory safety features prevent entire classes of bugs like buffer overflows and null pointer dereferences that can cause serious issues in production systems. With embedded devices becoming increasingly sophisticated and increasingly connected, this is more important than ever. What's particularly nice about Rust is that you get these safety benefits without any performance overhead. Zero-cost abstractions and predictable behavior, exactly what you need for real-time embedded applications. The compiler catches many mistakes at compile time, rather than letting them become runtime problems, which is incredibly useful. Raspberry Pi Pico 2's dual Cortex M33 cores work very well with Rust, and we put a lot of effort into providing comprehensive tooling and comprehensive documentation. And we've been collaborating closely with the embedded Rust community to make sure everything works properly. Thanks to Sean and the DigiKey team for creating this educational content. We're excited to see what you build with it.
Because of this backing and maturity, we'll actually be using the RP2350 in this series. It makes the experience of developing embedded Rust much more enjoyable. I want to give a special mention to the Zephyr project. They recently started adding Rust support to Zephyr, which means you'll soon be able to write Rust applications on top of the Zephyr real-time operating system, even though that's written in C. Rust in Zephyr is still new and only supports a few target architectures at the moment, but the promise of being able to write cross-platform Rust applications for a wide variety of microcontrollers is quite enticing. After all that, Rust sounds pretty amazing, right? Well, it's not without a few limitations that you should be aware of. First, Rust is a good deal more complex than, say, C. As a result, it can take some time to wrap your head around some of the syntax and features like the borrow checker. Because Rust is strongly typed, it can be quite verbose, and you will often spend time debugging compile time errors to make sure your code passes the borrow checker to be memory safe. This means that development time can be slower than with other languages. Rust also has notably longer compile times than other languages due to the borrow checker doing extra work, having to generate copies of generic code known as monomorphization, and dealing with traits, which is something we'll look at later. While Rust can create some impressively optimized programs, these longer compile times can be very frustrating when you need a shorter edit, compile, debug loop while writing code. And when I say optimized, I don't necessarily mean small. Rust boasts zero-cost abstractions and fast runtimes, but a few aspects of the language means you can end up with large binaries. The first is that Rust performs static linking to libraries by default, which means all libraries you use get pulled into a single executable. This is opposed to dynamic linking, where you can call functions in compiled binaries. Think .so or .dll files. Monomorphization can bite us here too, as generating code from generics means, well, more code. And like C++, Rust has a standard library that contains a lot of functionality, but it can add some bloat to your application. Luckily, these aren't a big deal in embedded systems, as we usually assume static linking anyway, and we won't be using the standard library, as it's often too big and complex for microcontrollers and assumes you have an underlying operating system. Monomorphization can still be an issue, so keep that in mind when we look at generics in a later episode. An application binary interface, or ABI, is the low-level specification that defines how compiled code components communicate with each other. This includes calling functions in other libraries, how are parameters passed in, and how data structures are laid out. Note that ABIs are specific to individual CPU architectures and operating systems. C has a widely adopted stable ABI, which means other languages can call libraries written in C through C bindings. It's one of the many reasons C is so widely adopted for things like operating system kernels, drivers, and system libraries. The Rust team has not standardized Rust's application binary interface yet, which means programs written in other languages cannot call Rust code directly. To work around this, Rust libraries must expose a C-compatible interface to be callable from other languages. This limits Rust's ecosystem growth, as developers want to be able to call Rust libraries from a wide variety of languages. That being said, if we're sticking to purely embedded Rust in our applications, we don't need to worry about this too much. It only comes into play if we're writing code in other languages for things like bootloaders or real-time operating systems and want to call Rust code from other languages. Speaking of embedded Rust, let's look at a few limitations that apply mostly to the embedded side. Using Rust for embedded systems is relatively new, which means board support and libraries are still mostly community supported, and immature libraries can have breaking changes from one version to the next. Luckily, the cargo system that comes with Rust can help a lot to manage dependencies and versions. Because Rust is still relatively new, there is very little adoption by silicon vendors, which means you won't find much official support on various microcontrollers. The exceptions are Raspberry Pi, Espressif, and ST Microelectronics, as we saw earlier. They're slowly starting to support Rust. There's also limited drivers and libraries. You'll likely find that you'll need to rewrite C libraries for talking to things like sensors. Complex drivers like graphics, Wi-Fi, and TCP/IP are also very new and likely buggy. While you might not need a real-time operating system for simpler projects, they are very popular in industry for handling complex workloads. Unfortunately, there's no mature RTOS for Rust yet. Your two big options right now are Embassy and Real-Time Interrupt-Driven Concurrency, or RTIC. Neither is a fully featured RTOS. Embassy is an asynchronous framework, which means it doesn't really have preemptive scheduling like you might be used to. And RTIC is a concurrency framework that does provide preemptive scheduling, but it lacks a kernel and dynamic memory allocation that you'd find in a traditional RTOS, should you need those. Both are very technically capable, but their ecosystems are still growing and lack industry adoption right now. Finally, as you can probably guess, there's a much smaller knowledge base and community support than you might find for embedded C, which has been in use for decades. There's not a lot of hardware you'll need for this series. You should get a Raspberry Pi Pico 2 or Pico 2W if you want to try Wi-Fi later after the series. You'll also need an LED, 220 ohm resistor, a push button, and a TMP 102 I2C temperature sensor breakout board. You'll also want a breadboard, some jumper wires, and a USB cable. That's it. Most of our work will be understanding how to build Rust applications, use Rust features like borrowing and generics, and creating some demos around quintessential embedded concepts like interrupts, debugging, and asynchronous execution. My hope is that these give you the building blocks and experience needed to start confidently writing your own embedded Rust applications. Now, let's see how to set up the pre-configured Docker image and build a simple Hello World application in Rust. Note that we won't even touch embedded Rust yet. We'll save that for the next episode. If you'd like to install Rust locally rather than use the provided Docker image, you're welcome to do so. Just go to the rustlang.org website and click Install at the top. Follow the instructions to install Rust for your particular operating system. If you want to use the pre-configured Docker image, then you need to make sure that you have Docker Desktop installed and running on your computer. Go to docker.com, click on Download Docker Desktop, and choose your operating system. Follow the instructions to install Docker Desktop. While you can edit the files mapped to the container using whatever editor you'd like, I highly recommend installing VS Code locally, as that's what I'll be showing. To start, head to github.com/seanhemel/introduction to embedded Rust. This is a repository that contains the Docker file to build the image for us that we will use for development, and it also contains a bunch of example apps that we're going to create throughout the series, our library, and it will create a Rustlings folder that you will see in a moment. Go to Code and click Download Zip somewhere on your computer. Go ahead and unzip that once it's done. In a terminal, navigate into the Introduction to Embedded Rust folder that you just unzipped. Make sure Docker Desktop is running in the background, and enter docker build-t. Give your image a name. We'll call it env embedded rust. I recommend using that name so that it lines up with the name that the VS Code dev containers extension is expecting. And then don't forget that period at the end, which tells it to use the current directory as the context for how to build this Docker image. Give it a moment and let that build. You have two ways to interact with this image. The first way is to call this docker run command. Give it --rm to remove and clean up the container when you exit it, -it for interactive mode, then -p to forward the port 3000 to 3000 on the host machine. The image comes preloaded with the Rust book in case you need it, say, on the road or flying and you don't have access to the internet. Also forward the port 33033, which we will need for debugging later on in the series. We'll want to map the volume, so with -v, give it the current working directory, the workspace directory, map that to home student workspace in the container, and then let's make the working directory home student workspace. As you can see, I forgot the actual image name. So don't forget the image name, env embedded rust, that we just created. You should see student at some hex value. This means you're actually running the image and you're inside the container right now. You can see the available workspace that we mapped here. Note that anything in workspace is saved to the host machine, so you can save your work as you're going on and then copy that out or use it as a reference later. So when you close down the container, anything in workspace is not deleted. That's saved on your host computer. You are welcome to use any editor you'd like. Inside that workspace, write code and then call commands in this terminal. My recommendation is to use VS Code. So install that locally on your computer. And for the extension, you will want dev containers. This is the only one we will need right now because anything else inside the container will be installed for us. Down in the bottom left, you should be able to click this Open a Remote Window button. And with that container running in the background, you can click Attach to Running Container. It should pop up with the container name. Make sure the image is correct, the env embedded Rust image. Click that. It'll open up another window for you. So feel free to exit out of this. It will do any necessary configuration. It will first ask you to load the workspace, default.code workspace that comes preloaded with the image. Click that. Give it a moment. It should try to install any necessary extensions. So the ones that we need for this are Cortex Debug, that comes with some dependencies, such as debug tracking, peripheral view, and so on. The big one we'll need is Rust Analyzer, and that should come pre-installed in this image. The other way to interact with this container is to first close this running one. So in here, we will just type exit. That exits out of the container, and because of that -rm flag, it should clean it up for us, meaning it deletes the whole container. Once you've built the image, you shouldn't need this shell any longer, at least for this episode. Bring up a new window for VS Code, go to File, Open Folder, go into the repository that you downloaded and unzipped. That will be our folder. Make sure you have workspace in there because that's what's going to be mapped to the container. Select Folder. You should get a pop-up here saying, hey, we found a dev container configuration file. Do you want to reopen it? Feel free to click that to reopen it. That's probably the easiest way to do it. If that pop-up goes away, you can click this Open a Remote Window button, and you can just say Reopen in Container. Not attached to running container because we don't have a running container. Reopen in Container. That actually spins up a new container based on that image in that configuration file in that workspace or in that folder. Again, it's going to ask you to reload the window and open the workspace. Feel free to go to File, Open Workspace from File. In Workspace, you should see this default code workspace that provides some basic configuration and make sure that you have the correct folders viewed here that are mapped to your host machine. You will likely see a warning that Rustlings doesn't exist. We will create that in just a moment. Again, if you go to Extensions, you should have the Cortex Debug extension installed. If you get a pop-up saying that one of these didn't install, one of the dependencies did not install, feel free to click Reload Window. That should be fine. And the big one we'll need is Rust Analyzer. Again, if you're using the Docker image that comes with the repository, this should be pre-installed for you. Let's close out of that window. Now let's go into our files. Let's create our first Rust app the manual way. So in apps here, we're going to store all of our apps throughout the series. In fact, if you downloaded the repository, this will probably be filled out for you, but we're going to recreate them throughout the series. Feel free to reference those or delete them and follow along. Let's create a new folder under apps called Hello World. In here, we will create another folder called src for source. In source, we will create main.rs. .rs, of course, for Rust. Like with any good programming language, we need an entry point. Rust looks for this main function to use as the default entry point. Functions are denoted by this fn keyword that says anything that comes after it is a function and treated as such. We don't have any parameters for this function signature, and we include blocks of code in these curly braces, much like you've seen from things like C and C++ and Java. To print something to the screen, we will use this println macro. You know it's a macro because of this exclamation point. So anytime you see that, it's a macro, not a function. This macro comes included in the standard library in Rust. Because we are running this in an operating system, the standard library is included by default, and we have access to things like this macro. When we compile this, it automatically figures out how it needs to link to and include the correct dependencies for outputting to a console, regardless of which operating system you are on. That is, of course, assuming that Rust supports that particular operating system. So your major ones, Linux, Windows, Mac OS, it should have support for, and this println macro should work. When we get to embedded code, this is going to be much trickier because we won't have access, or we will choose not to include standard because we don't have an operating system, which means this macro won't work for embedded systems unless you include a very specific embedded version of it. but we will explore other ways to print out to a terminal in later episodes when we are working with embedded systems. Next, type hello world in quotation marks. We will pass this string in as an argument to this macro. This string literal looks the same as you would expect in C, C++, and Java, just in double quotation marks. We will end this statement with a semicolon, much like you find in C and C++. This helps the compiler parse the different statements, so you can actually continue on this line if you want with semicolons, but in general programming practice, we include different statements on different lines, but make sure that you end each statement with a semicolon. Let's save this, so File, Save. Let's go down to our terminal. When we open a terminal, this should default to Apps. So ls to see what's in there, we see our Hello World folder. Let's go in there, and we will go into the src directory. We didn't need to make an src directory, but when we get to using cargo, you will see why in a moment. So there is our main.rs file. Rust.c is the Rust compiler that comes bundled with Rust when you installed it. Even if you did this locally, when you install Rust, it comes with Rust.c. We will simply give main.rs to Rust.c. That will compile our code. And if we look at the available files, sure enough, we see the main application here. Just like we could if we created an executable using something like GCC, we can run this with /main, and you should see hello world printed to the console. Let's go ahead and get rid of that executable. As I mentioned, Rust.c is the actual Rust compiler, and we just called it manually here. What we've created is a very basic crate. This is the smallest amount of code that the compiler will process in a single compilation. It can be a binary crate, which is what we created here, which is an executable. Because we have this main, it creates an entry point. Or it can be a library crate, which is a dependency to be imported in other crates. Going forward, we're actually going to rely on the cargo meta tool. This is a very powerful build system and package manager that also comes bundled with Rust. So to use something that cargo understands, whether it's a package or a component, we actually need to create this package by creating a new file in our hello world directory. We will call this cargo with a capital C .toml. TOML here stands for Tom's Obvious Minimal Language. It's just another markup language that's popular with developers, system administrators, and various frameworks. But it is what Cargo uses for all of its configuration files. Notice we have cargo.toml. We have a source directory with our code in here. Unless we specify differently in the configuration file, Cargo will, by default, look for code in this very specifically named src folder, and it will also look for this main.rs to determine that this is a binary crate and it should create an executable. So this naming is important unless you specify something else to Cargo. In our cargo.toml file, we're going to create a section which is denoted by this name in brackets. So anything under here belongs to this package section. And like other configuration files, this is mostly a collection of key value pairs. So we have the key name equals hello, which is the name of our package. We'll give it a version, in this case 0.1.0. When you initialize something using Cargo, it likes to set this version to 0.1.0 by default, so we'll start there. You also have to specify the version of Rust you're using. They use the term edition so that you're not confusing it with a version of, say, your package or a particular dependency. An edition is like, say, a version of Python. It's a particular collection of language features and rules that have been released, and a new edition of Rust comes out once every few years. You could use something like a nightly build, but I recommend sticking to one of these more stable editions. 2024 is the latest stable edition, so we will stick with that for the series. You will also come across some dependencies, especially for embedded code, that uses the 2021 edition. One of the interesting things about editions is that Rust does a lot of work to maintain some level of backwards compatibility, which means that, say, in our Hello World app, or we create another app, we include dependencies, we list them out in cargo.toml. Some of those dependencies might have been written with a different edition of Rust. Rust generally guarantees that you can build those packages using that edition. So maybe some library we use was built with edition 2021. We can write our app in edition 2024, and the two will operate together just fine. If you're coming from, say, the Python world, you are probably familiar with dependency hell, where the different versions of Python would break some packages and you would have to find a version of Python that worked with everything. So that is one of the major benefits of going with Rust. This edition is very nice. It guarantees some level of interoperability among the editions. You should also list out your dependencies, and in fact, we are going to include this as a section header here. Later, we will fill this out as we include embedded libraries for our project. But this creates a bare minimum cargo.toml file that we need so that we can use Cargo to build and run our code. Let's save this. Let's go down to our terminal. Let's go up a folder. So we should be in that Hello World folder where we can see cargo.toml and source. And we are going to say cargo build. Cargo build does all of the heavy lifting to call the compiler, or Rust C, on the back end. It will download any of the dependencies you list if you need to download them, build those dependencies, and link them to your, in this case, application or library if that's what you're making. This is a very powerful build tool. If you're coming from something like Makefiles or CMake, this is so much easier to use than having to custom create things like CMake files or Makefiles. Let's go up here and refresh our files. You can see that Cargo puts everything in this target folder as it builds. So this is our temporary, say, build folder. It contains artifacts from the build process, and it contains our built target. By default, it uses the debug profile, or dev profile, and it puts all of the artifacts in here, and you can see our executable hello here. So, /target debug hello, and notice that the name of this executable came from the name of the package we specified in cargo.toml. This allows us to run the executable directly from that debug folder. As you can see here, we've printed hello world to the screen. Instead of having to dig through those folders to find that executable, we can also say cargo run. That will find that debug profile for us, find the executable in there, and automatically run it. Note that if the project needs to be built, cargo run will build the project. I'm assuming it does some sort of diff on the back end to see if you've changed any code. Sure enough, it builds it and it runs the project. You can also type cargo clean. This essentially performs the very easy step of deleting that target folder, which you can see is now gone from our Hello World folder. As I mentioned, cargo build and cargo run assume you mean the debug profile. We can specify a different profile with --. So I'm going to say cargo build ---- release. That's going to build a release profile version. As you will see later, in our cargo.toml file, we can specify different compiler and linker flags for the different profiles here. So maybe for debug, we want to have better symbol tracking and we want to enable certain outputs. We can do that here versus the release profile where we want to say optimize for size or optimize for speed and remove any of those debug symbols to create a smaller binary. We will explore that later, but know that you can easily add different profiles for debug or release or any other profiles you want to create yourself. Let's come up to our files. Let's refresh. Let's go to target. Sure enough, there is no longer a debug folder here. Instead, there is a release. So if we go cargo run, it's going to automatically build for this dev profile because we did not specify a profile here. Let's refresh our files. Sure enough, it now has debug and release. And it went ahead and ran that hello executable in debug. As you can probably guess, we're going to say cargo run and give it the profile we want. In this case, ---- release. It sees that the release application has already been built and it runs that application in release for us. As your programs grow in size and complexity, something you will often run into is that Rust can be very slow when you build your project. There's a lot of things going on in that build step under the hood. Rather than sitting around and waiting to see if you get any compiler errors, you can run this command cargo check. This will essentially compile all of your packages and dependencies without performing that final step of generating your output code or your output binary. You will often find this is faster than cargo build, and it's a great way to shorten that write, check, fix errors loop. So we will run this. You will see it does it automatically for the dev profile, and we have no errors. With that, we are done demonstrating a basic Hello World app in Rust. As I mentioned, this is for running Rust with an operating system like Linux. We will be moving away from this to do embedded code, starting with the next episode. As you will see, it's going to get a little bit more complicated. Let's close out of these files, and let's turn our attention to Rustlings. Rustlings is a collection of exercises that goes along with the Rust book. So let's go to our workspace. This Docker image comes pre-installed with the Rustlings tool. So type Rustlings and then init. That's going to create the directory Rustlings in the current directory. So just press enter to continue. You should see initialization done. If you refresh your files and then drop down Rustlings, you should see this folder now filled out. Remember that this is on your host machine, so your progress in Rustlings should be saved, unless you decided to put Rustlings somewhere else in this container, in which case you might lose it. So I recommend keeping it in that workspace directory. If you go into exercises, you can see it's a collection of sections here. So let's go into intro. We will bring up intro 1. The general idea of Rustlings is to fix any compiler errors you might find in these example programs. The first one, intro 1, does not have any errors. It's just to demonstrate that everything works. So to check these, rather than trying to compile them yourself from the Rustlings directory, so cd into that, you can just run Rustlings. Note that Rustlings will often require Rust Analyzer on the back end to run, which does come pre-installed with this image, but I find it struggles in a Docker container. It will automatically try to analyze your code in real time without you pressing anything, but I actually like manual run anyway. So type -- manual -run. This runs Rustlings in manual mode. Feel free to read these instructions. Press enter to continue. It will do its best to pick up where you left off, so it tries to remember the last thing you were working on. It will start in these exercises 00 intro and intro 1, which is the file we have up here. You can see that it says exercise done, which means there are no compiler errors. If you'd like to run it to check, you can use these hotkeys here. You can even get a hint if you press H. So in manual mode, we press R, it will run it. Sure enough, it still works. So we're done with this, which means we can press N for next, and then that refers to intro 2. So we open up intro 2, and sure enough, this one actually has an error. So read the instructions up here. This says to fix the code to print out hello world. Do what you need to fix that. And then in the terminal, press R to run it again, and you should see that exercise done when you have fixed that error. Press N when you're done. Notice you can't press N right now until you fixed it to move on to the next one. If you go into exercises, scroll down, you should see README. Let's close out of this terminal. Actually, we can press Q to exit out of Rustlings, X to exit out of the terminal, and you can see this exercise to book chapter mapping. These are the various chapters in the Rust book and how they map up to the exercises. Notice that it's not always necessarily in order, so pay attention to which book chapter refers to which set of exercises that map over here. If you need access to the book and you don't have internet, you can actually go to localhost :3000, assuming that the container is running on the back end for you, and it is hosting a version of the official Rust book. So feel free to work through these. At the end of many of the episodes, especially in the beginning of the series, I'll give you recommended chapters to read. I recommend reading through those because it will help you understand parts of the language, and then we will see them in use in the following episode. Additionally, I will recommend some rustling exercises to do, so you can put those concepts into practice. We are all done here. So when you are done with the container, you can just exit out like that. If you were working in a terminal and you had the container running that way, you can just type exit like we did earlier, and that should clean up the container for you. I hope this helps you get a better understanding of the current state of Rust for embedded systems and where you might run into some limitations. In the next episode, we'll actually set up an embedded project for our Pico 2 and Blink and LED. Before then, I recommend reading chapters 1 through 3 in the Rust book. These walk you through the Hello World exercise we just did, help you get a feeling for writing a basic guessing game, and understanding some of the basic concepts like variables and functions. I also recommend doing the first 3 sections of Rustlings exercises after the intro. These test your knowledge of variables, functions, and if statements. Good luck with the exercises, and I'll see you in the next episode.